achieve higher RRR or or a good quality of a film. Same thing here. So basically, you can also probe the region of the RRR with the different bias energy, the bias voltage as well as the temperature. Now to something that it interests us a little more. It's the niobium on copper deposition, and you'll see again. If you look at the SEM pictures, you have some grains over here that actually they look like they're niobium grains, but they actually are the mimic of the underlying substrate, the copper substrate. And you see this kind of grain growth domains as well. Okay, so we have done deposition on single crystal substrate on 100, 110, and 111. And we have verified that with all the, at all bias voltages, we're actually growing the films in respect of the heteroepitaxial relationship between niobium and copper, which means that we're growing niobium 110 on copper 100, niobium 100 on copper 110, and niobium 110 on copper 111. Of course, this is without the oxide layer at the interface. Okay, same thing here for the different bias voltages. This is a high-resolution TEM for a niobium film coated on an oxidized copper interface. And you can see at the bottom the interface that is relatively sharp, and the niobium oxide layer that is about 5 nanometer thick in all cases. As we increase the energy, we actually increase the quality of the film. We grow films that have a lower defect density and are also smoother. This is also, again, for niobium on oxidized copper. Same thing here. When you grow a film, start growing a film at 120 volt bias, you have the 6-fold symmetry that Josh talked about on Monday. And as you increase the time up to 45 minutes, you actually see that this goes away, and one of the growth domain is taking over. The same thing for the niobium on copper metallic. It means that the oxide has been reduced. And this is a typical substrate as seen by EBSD. And on each side, you have an EBSD map for, in one case, a bias at 120 volt, and here a case at a bias at 0 volt. And you can see that you have two different ways of growing the niobium. Here, if you remember one of the slides at the beginning where I was showing you what abnormal growth looks like, it looks like it is. We are actually growing with the abnormal growth mode. The gray points correspond to points on the map that had a confidence index of less than 0.1. So this is another thing with the, as function of the bias voltage, and you see as you increase the bias voltage, you actually get rid of some of these smaller grain due to abnormal growth. Okay. This is some EBSD map grown for large grain copper. And finally, some RF results that are very preliminary because we only managed to measure 3 of the samples before we had to come for the workshop. One of them was deposited on an oxidized copper, which is actually the green one right over here. And the blue curve and the red curve are films that have been deposited at 120 and 150 volts at 360 baking and coating. The black curve shows you the behavior in this instrument for a fine-grained niobium sample. So you can see that we still have some ways to go. The RRR of this one, actually I have it as the green curve, the RRR was 8, and this was in the hundreds for both. So that reminds me of the behavior of the niobium on copper cavities from CERN. that have been done some years ago. Okay, welcome to in conclusion of copper substrates. We have verified the heteropyridiaxial relationship between niobium and copper and with the ECR process. And we have also grown films both on oxidized and metallic copper surfaces. And we have shown that as a function of the bias voltage, as well as the baking, preheating temperature, and coating temperature, we can tailor the structure of the film from columnar growth to equiaxial growth going through also abnormal growth. Of course, we will be only able to verify that by doing cross-section with EBSD and looking at the underlying substrate as well as the cross-section of the film. And we should do that with EBSD and TEM, or TEM for the finer grain for copper, EBSD for the larger grain, because if not, you would be able to only see one grain in the TEM analysis. And we also need, all the triple R measurements that we have done were done on sapphire. That's not copper. So we definitely need to do the measurements, the triple R measurement for films that have been grown on copper to make a direct correlation with the SRF performance. And finally, general conclusion. So we, in the context of this collaboration between JLab and the surrounding university, we are pursuing, trying to understand better the growth of niobium in the hope that we achieve a bulk-like performance in terms of SRF. And we definitely want to develop this. We have grown films on a variety of substrate. The goal to do that is actually to try to understand how the film grows and how it behaves according to different conditions. We have been able to achieve high triple R values, and we have some evidence that we can actually tune the structure of the film by playing with the bias energy, the bias voltage, as well as the temperature, which would allow us, for example, to achieve the same results that we would achieve with temperature that are much higher if we were only dealing with thermal energy. And that's it. This is the list of the people that are involved in the different aspects of this collaboration. And this has been funded under the DOE HEP grant and JLab contract with DOE. Thank you.